Alright, in this video we're going to talk about gases, a little bit about what they are and how they behave. So the first thing to know about gases is that they're fluids, and what that means is not that they're a liquid. Sometimes the word fluid gets kind of misused a little bit to mean to be synonymous with liquid, but all a fluid means is something that flows. So gases are able to flow. If you, let's say, puncture your bike tire and you have a hole in it, gas is going to flow out of that hole. So in terms of gases and how they behave, you want to know that they have low density. So what that means is that they're very sparse. So there's a lot of empty space. There's a lot of space between the molecules, and the volume of a gas is taken up mostly by empty space. And this is a really important point here that we're going to elaborate on later. But basically, if we have some container and we have some gas particles in it, the majority of the space that's taken up in this container is not made up of particles, it's just made up of empty space. Not matter, just again empty space, not any sort of molecules or atoms of the gas. So the volume, the percentage of the volume of this container that's taken up by actual gas molecules is very small. So we have, again, the majority empty space. That's very important here. So the next thing to know about gases, and this kind of relates to the first 2 points, is that they're highly compressible. Highly compressible. That was a terrible circle, but highly compressible. So basically this kind of has to do a lot with the fact that they're mostly empty space. So if we have some gas particles in here and then we have mostly empty space and we try and compress the volume of this container down, it's going to be a lot easier to do because we have mostly empty space. Whereas let's say we take a solid chunk of aluminum or something like that and we try and compress it, it's going to be pretty hard to do because the aluminum is going to have a bunch of molecules packed really tightly together in here. There are going to be strong forces in between there that are going to prevent this from being compressed. Whereas a gas, because we have mostly empty space, it's actually going to be pretty easy to compress most gases. So the last thing to know about gas is that they completely fill their container. So if we have like a liquid, let's say, a liquid takes the shape of its container, but it doesn't completely fill it up. Like if we take a jar and fill it halfway up with liquid and we seal off the top, the liquid doesn't expand to take up the entire volume of the container. It only takes up the part that the liquid's volume would take up. Whereas a gas, if we put a gas into a container and seal it up, the gas is kind of going to flow around all in this container and take up the entire space. So a gas completely fills its container, and that's an important point to know here. So in terms of what gases look like, this is a pretty good representation of how you want to envision a gas and gas molecules. So it's basically just a container with a bunch of empty space, and then we have some gas particles here, and they're all moving around. Remember, we said that temperature tells us how fast particles are moving. Any matter that has any sort of temperature at all, which is everything, is going to have some sort of motion of the particles. So with a gas, we're usually at higher temperatures. There's going to be a lot of motion of these particles. They're going to be moving around in straight lines here. If they hit the wall of the container like this, they'll bounce off and start moving in a different direction. So realistically, you would probably want to imagine these particles as like very small, like maybe tiny dots like this moving around. But just to see kind of that gases are made up of particles, this is a pretty good representation. When we walk through air, let's say, it's air is made up of particles, so that's why wind resistance is existent, because we have particles that we're moving through. If we were going through a vacuum, there would be little or no wind resistance in there. Well, there would be no wind resistance, but so these particles are that kind of tells us that air is made up of particles. Alright, so the next thing to talk about here is pressure. So we've heard of probably atmospheric pressure. So that's kind of similar to what we're going to be talking about with gases here. So what pressure is the force per unit of area. So I have nail versus dowel here. What I mean by that is if we take a nail, kind of shaped like this, and we try and, let's say, punch it through a board of wood, and we hammer it down, this is a very small area here. So we're giving it a certain force with the hammer, and we're trying to nail it through this board, and it's going through this very small area. So pressure is force per unit area. So if we have this very small area, let's say with a hammer we're giving it a force of 100. We're not going to talk about the units for force, they would be newtons for any of you who have taken physics, but let's say we have a force of 100, and the area of this nail, let's say, is 0.001 or something along those lines. This would give us a very large pressure. This would give us a pressure of, I think it would be 100,000. Right, so this would be a very large pressure. Whereas let's say we take the same piece of wood and we're trying to puncture it with a wooden dowel that has maybe a area of, let's say, 1, whatever units we're talking about here. So the pressure would then be, we're going to put the same force on this dowel from a hammer or whatever we're going to bang it into the wood with. So we're going to have 100 for our force, and then this time the area is 1. So this is only going to give us a pressure of 100. So the dowel, this is why a dowel would not really puncture wood if you tried to nail it into it unless you nailed it really hard, whereas a nail goes in pretty easily, right? So it's all because of the pressure. It's also a similar concept to if you've ever seen anyone lay on a bed of nails. Basically, if you tried to lay on one nail, it would puncture your skin and hurt really bad, but if you have a bed of nails, you're basically increasing this area here. By increasing the area like we showed here, we're going to decrease the pressure. So if you have an entire bed of 1,000 or a few thousand nails and you lay on that, you're really increasing the area that force of your body, of the weight of your body, is distributed across. So that's why people can lay on a bed of nails and not kill themselves. So in terms of gases, the pressure of a gas is caused by the collisions between the molecules. So we looked at, in the last slide, we looked at this representation of gas molecules as just flying around in this container with this straight line motion, and basically in terms of pressure, those collisions between the particles themselves or the particles in the container, that's what's going to cause the pressure. So it's very important to know that pressure is caused by collisions between the molecules. And then the last thing to know about pressure here is just the units: atmospheres, pascals, kilopascals, all units you want to know for pressure. On your reference table, if you look at table A, it tells you standard temperature and pressure, STP. We've talked about that before. This is 1 atmosphere, or 101.3 kilopascals, and that would be standard pressure. So atmospheres, kilopascals, you want to know both of those units in case you come across them in any sort of gas problem. So kinetic molecular theory is basically this representation of how particles act. So there's 3 important concepts here. The first is that matter is made up of particles that are in constant motion. So just kind of like we had that diagram of the gas particles kind of flying around in this straight line motion in the container, right? This is how you want to think of particles moving. So matter is made up of particles that are in motion. That's an important thing to know. The first tenet of kinetic molecular theory. The second one is that particles are attracted to each other. So when we have a gas, these particles are going to have some sort of attraction for each other. And the farther particles are apart, the weaker the attractions are. So a gas is going to actually have weak attractions compared to, let's say, a solid where the particles are all close together. This is going to result in a lot stronger attractions, basically. Again, the farther away the particles are from each other, the weaker those attractions are going to be. So then the last thing here, and this should say number 3, I'm not sure what happened there, but the higher the temperature, the faster the particles move. So we talked about what temperature is. It's a measure of the kinetic energy of the particles. So kinetic energy is proportional to temperature. So if something is at a higher temperature, the particles are going to be moving faster. They're going to have more kinetic energy, because that's what temperature means, is how much kinetic energy we have. And kinetic energy is telling us basically how fast the particles are moving. So the higher the temperature, the faster the motion of those particles. Alright, so the next concept here is of ideal gases, and this is important to know, all of these characteristics of an ideal gas. So an ideal gas is this conceptualization of basically how we can represent gases and how they act. It's not perfect, there's no such thing as a perfectly ideal gas, but we can get pretty close because gases generally follow these characteristics. So we already said in kinetic molecular theory that the ideal gas particles are in constant random motion. This just follows straight from kinetic molecular theory, that we have these gases in some container and they're just moving around in straight lines. So the second thing we're going to say here is that gases are very far apart from each other. So what that means is that if we take the gas particles and we put them in a big space, and we take these tiny little particles, we're saying that they're so far apart that the volume of the particles is considered negligible. So in terms of negligible, meaning that it's insignificant, it's so small that we can ignore it. If we look at a big space like this and we put a few tiny gas particles, they're almost not noticeable. So that's what we're saying here, is that because the gas particles are so far apart, there's so much space in between each of these particles that their size is negligible. So along those lines, again, with how far apart these gas particles are, they're going to have no attractive forces between them, and this is very important. So if we said in kinetic molecular theory that the farther apart particles are, the weaker the attractions are going to be, here we're saying that the gas particles are so far apart that they're going to have no attractive forces between them. So two important things here for ideal gases. They have no volume, or negligible volume, and they have no attractive forces, or no attractions. So this is very important to know about ideal gases. So the last thing here, the gas particles can have collision that may result in energy transfer, but not a loss or gain of energy. This basically just follows the law of conservation of energy, that if two gas particles run into each other, they can transfer energy to one another, but they cannot gain or lose energy as a system. But realistically, the two major things to know here are that ideal gases have no volume and no attractions. So when are gases closest to being ideal? At high temperatures and low pressures, and this is important to know. What this is going to give us, both of these changes would result in a high volume. So if we think about high volume, why that would make gases most ideal, well, if we have a high volume, that's going to make the gas particles farther apart from each other. If we take a few gas particles and put them in a big space like this, or if we take a few gas particles and put them in, let's say, a small space like this, here the gas particles in the smaller space are taking up a larger percentage of this container than they are of the large container. So they're a lot closer together, which means that the volume of the particles is more significant, and there's also going to be a lot more attractive forces here when these are closer together. So if we want them to be more ideal, we want them to be in a bigger space so that they have lower attractions, closer to no attractions, and their volume becomes less significant when we put them in a bigger space. So high temperatures and low pressures lead to a high volume, which makes gases behave most ideally. So we've got a couple of questions to think about here. As we increase the volume of a gas's container, what will happen to the pressure? So if you want to pause the video and take a sec to think about this on your own, you can do that. I'll explain it now. The gas particles, if we increase the volume of the container, we expand the walls of this container out, we're basically giving these particles more space to move around. So what's going to happen to the pressure? The key with pressure is we were talking about the collisions between the molecules. So if we increase the volume, we give these gas particles more space to move around, they're not going to have as many collisions. So if there's fewer collisions, that's going to lead to a lower pressure. So a lower pressure if we increase the volume. And so if you can kind of envision what we did here, we expanded the volume. These gas particles, there's going to be a lot more empty space for them to roam around in, therefore they would run into each other less. And fewer collisions, because collisions are what cause gas pressure, fewer collisions would give us a lower pressure. So the next question here, if we have a gas and we increase the temperature of the gas, what will happen to the volume of the container? If we take a flexible container like a balloon or something and we put some gas in there and then increase the temperature, what's going to happen? So again, pause the video if you want to think about this on your own, but what's going to happen is if we increase the temperature, remember, is telling us the average kinetic energy of the particles. That's what temperature tells us. So that's basically, again, how fast the particles are moving. So these, if we increase the temperature, these gas particles are going to be moving around a lot faster here. They're going to bump into the walls of this container harder, and they're going to bump into it more. So that's going to kind of cause this container to want to expand out like this because of all these collisions with the container walls. So in this case, the volume will increase. If we increase the temperature, the volume will increase again because we're going to have these particles colliding harder and more often with the walls of this container. So the last question here, if we increase the temperature of the gas, what is going to happen to the pressure of the gas? So this one should kind of follow pretty logically based on the last two if you've been following those. But again, pause the video if you want to take a sec to think about this on your own. So if we increase the temperature, again, we're going to be increasing the kinetic energy of the particles. We're going to be making these particles move faster. So these particles are going to be in this container flying around even faster. What's going to happen to the pressure of the gas? So again, the important concept with pressure is collisions. So we have these gas particles that are now going to be moving around a lot faster in here. So what's going to happen in terms of collisions? Well, they'll collide more and they'll collide harder. So the pressure of the gas, if we increase the temperature, would increase. Increase pressure would result from an increase in temperature. Alright, so if you didn't get these last three questions about relationships between temperature and pressure and volume, go back a few minutes and try and think about them again in terms of the collisions for pressure and the speed of the particles, the kinetic energy, for the temperature. Thanks for watching this video on an introduction to gases.